Okay, so we're testing for convergence of infinite series of sums that go on forever. Okay, so the first test is really, really simple. Okay. Okay, so let's look at any infinite series. Suppose we have a sum where n goes from we'll go from 0 to infinity, doesn't really matter how I index it, and say it's the sum of terms called a to the n, okay? A sub n, okay? Well, the first one is pretty simple, okay? Remember, this is going to be equal to the limit as, we'll say, k goes to infinity, and we have of this sum, the sum where, I should make that an n actually, forgive me. We'll call this the limit as n goes to infinity, and we have now a sum to n. So we have the sum goes up to n this time, and we have k goes from 0, ak like that. Okay, so I've changed the index, but this means I take the sum of the first n many terms, okay, or n plus 1 or whatever it is, but the first group of terms, and then I take the limit of that sum as n goes to infinity, which is of course the limit for the partial sum Sn. Okay. Well, here's the important thing. Okay. The only way this can start to approach any value, okay, is if these terms here, a sub n, start going to 0. Okay. So first test. Is as follows. Okay, it's as follows. If the sum converges, then the terms a to the a sub n must go to 0. Okay, as n goes to infinity. Okay, they must go to 0 as n goes to infinity. So for example, we saw this, we had the geometric series, we had 1 plus 1 over 3 plus 1 over 9 plus 1 over 27 plus all the way, which was equal to the sum where n, well, we'll start from 0 in this case, that was 1 third to the power n here, starting at 0, that makes this work. And this one, we can see here that the terms are all themselves getting smaller. They're all going to 0 as n gets bigger. This one potentially converges. It may not converge, but it would potentially converge because the terms are going to 0. But satisfies this condition. Okay. However, let's take another example here. Let's have the sum. We'll have n goes from 0 to infinity, and let's take something a little bit more, a little bit trickier. Let's take something like this one. Yeah. What does that do? Okay. Well, the first term looks like this. Okay, the first term has n equals 0. So it's minus 1 to the 0. So that's 1 plus 1 is my first term. My second term is 1 minus 1. Okay, or I should say my 0th on my first term. Then it goes 1 plus 1, and then it goes 1 minus 1, like that, forever. So this always looks like 2, 0, 2, 0, 2, 0, and it has this alternating behavior. Okay, and we can see that some of these are 0, but they don't consistently all go to 0, right? They don't consistently all go to 0. And if I were to sum, this would either be 2 or 4 or 6 or 8, and it keeps going up, okay? Because there will always be another 2 somewhere. There will always be another 2 coming. I might be on a 0, but the next term will always be 2, okay? So this one fails. And it's clearly, it should be a plus actually here, plus, plus, plus. Okay, so these are the terms, plus, 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 plus. Okay. So this one goes 2 plus 0 plus 2 plus 0 plus forever. It fails and it cannot converge. Okay. As I get bigger, the sum keeps getting bigger. Okay. But there's a bit of a complication here. Okay. Test 1 does not prove convergence. What do I mean by that? It is possible that the terms go to 0, but that the sum diverges. And there's a very important example which is called the harmonic series. The harmonic series, it has something to do with overtones in music, but it's not really important to think about. The harmonic series looks like this. It goes 1 plus, then 1/2, then 1/3, then 1/4, then 1/5, and so on forever. And if we write that, this would be the sum to infinity, where n goes from 1 to infinity, and it's 1 over n, like that. Okay, so what happens here? Okay, n starts at 1, it gives me 1 over 1, which is this value here. Then n goes up to 2, which gives me a 2 on the bottom, that gives me 1/2, and I have it here, and it goes on forever. And we can clearly see that 1 over n is going to 0. 1 over n does go to 0. As n goes to infinity. Okay. However, and this is the really important thing, this does not converge. The harmonic series diverges. Okay. It goes very, very slowly, but believe it or not, if you sum up all of the terms, the infinitely many terms here, in this one, you don't get a finite number. It keeps going towards infinity. It just goes very, very slowly towards infinity. Okay. So we're going to need another test for convergence, something which works a little bit better. Okay. So we have something called the ratio test, or the D'Alembert ratio test. D'Alembert. ratio test. D'Alembert was a mathematician. The test is actually, it's quite hard to prove that it works, but actually doing it is not that bad. Okay, so here it is. Okay, so we consider, suppose we have a series and the series goes as follows. Okay, it's u1 plus u2 plus u3 and so on forever, which is equal to the sum of un, where n goes from 1 to infinity. Of course, u here could be called a, or it could be called t, or it could be called absolutely anything else. It does not matter. Okay. Here we're using the terms u, doesn't matter, but that's what we're doing. Now, what do? We consider the ratio. And the ratio should be as follows. The ratio should be the absolute value, okay, of un plus 1 over un as n goes to infinity. Okay, so un plus 1 here means the n plus first term, not un, the term, and then add 1 to that term. I mean the nth term and the n plus first term. That might be a little bit difficult to see here in my handwriting, but I mean nth term, n plus 1th term, or n plus first term, whatever that is. Okay, now there are three possibilities. Okay, the first one, okay, is that the ratio un plus 1 over un, okay, is less than 1, okay, which means it's a number between 0 and 1, okay, then convergent. Definitely convergent, okay. Provably convergent, okay. Second one, we can have that the ratio un plus 1, n plus first term over the nth term, we could have that is bigger than 1, okay, well then divergent. Okay, so that's almost every possibility. We have less than 1, we have bigger than 1. There's only one other possibility, which unfortunately happens more often than we would like, and that is that un plus 1 over un equals 1. Okay, well, what do we do then? Well, this is inconclusive. Okay, we don't know one way or the other. That is an inconclusive test. Okay, and that's unfortunate, but it happens. Okay, so we have another one here. This one's reasonably simple and straightforward. So we have a pattern here. Okay, we have an example. Okay, and the example is as follows. Okay, we have the progression here. We have terms 2n, 2 times n, minus 1, divided by 2 to the power n minus 1. Okay, and we're taking the sum of those, where n goes from 1 to infinity. Okay, so let's look at what those terms look like. Okay, well, 2 times 1 is 2. Take 1. I'm going to have a 1 on top there. What am I going to have on the bottom for the first term? N is 1. This is 2 to the power 1 minus 1. 1 minus 1 is 0. Anything to the power 0 is 1. So this first term is 1 over 1. The next term, I'm going to have 2n. 2 times 2 is 4. Take 1, that's 3. Okay, and then I'm going to have 2 to the power 2 minus 1, that's 2. Okay, and then we can see here that every single time I'm just adding 2 on top. So I would have 5 there. And then this one, the power goes up. Okay, so the power goes from 2 to the power 1. It goes from 2 to the power 2. We'll do one more term. 2 times 4 is 8. Take 1, that's 7. And on bottom, I have 4 minus 1 is the power. Okay, so that's 2 to the power 3. Okay, plus, and that goes on forever. Okay, so we can see here that this one is a little bit confusing. Okay, why is it confusing? It's confusing because the number on top is going up, but so is the number on the bottom. We have 1, 2, 2 squared, 2 cubed, and so on. Okay, so we need to work out, first of all, are these terms going to 0, which we could do, but we could just use the ratio test and that will give us the answer. Okay, so this is the example I'm going to do. Okay, so look at my expression here for my nth term. Okay, my nth term, un, is equal to what? That's 2n minus 1 over 2 to the power n minus 1. Okay, that is the nth term. What about the n plus first term? What's that? Well, then I replace n here with n plus 1, so that's 2 times n plus 1 minus 1. And then on the bottom, I have 2 times n plus 1 minus 1. Okay, we'll clean that up a little bit. This is 2n plus 2 minus 1, and this is just going to give me 2n plus 1. And on the bottom here, I'm just going to have 2 to the power n. Okay, so now my ratio is as follows. My ratio is un plus 1 divided by un. Okay, and formally I should include the absolute value as well. Everything is positive here, so it doesn't matter, but still something that should be considered and be careful with. What does that look like now? Well, that's going to be this second term, 2n plus 1 over 2 to the n, and we're going to divide that by this first term, 2n minus 1 over 2 to the n plus 1. Sorry, n minus 1. Okay, that's my situation there. And of course, when I divide fractions, I flip the second one upside down and multiply. So I end up with 2n plus 1, okay, is going to multiply 2 to the n minus 1. Okay, that's the top. Okay, and then on the bottom, okay, I put it the other way around, and I have 2n minus 1, and then I have 2 to the n. Okay, like that. And there is some cancellation that goes on here. Okay, the cancellation is relatively simple and straightforward. Okay, first of all, we can see here that this 2n minus 1 divides into the 2n on the bottom here, and I just have a power of 1, 2, a 2 to the 1 left over on the bottom. So this complicated thing, it breaks down to 2n plus 1 on top, and it's 2n minus 1 times 2. Okay. on the bottom. Okay. So let's multiply all that out. It's really not that bad. Okay. This is just going to be 2n plus 1 on top. And on the bottom, the 2n gets multiplied by a 2, giving me a 4n. Okay. And this minus 1 gets multiplied by a 2, giving me a minus 2. And now we find the limiting value as n goes to infinity. Okay, we find the limiting value as n goes to infinity. Okay, so how did we do this before? We divided top and bottom by the highest power of n that appears. The highest power that n that appears in this case is just n. Okay, so I've got 2n divided by n gives me 2, and then I have plus 1 over n, and underneath I have 4n gets divided by n and leaves me a 4, and then I have minus 2 over n. Okay, and what happens here as n goes to infinity? Well, the 2 stays the same, okay, but this 1 over n goes to 0, so this goes to 2 plus 0. And on the bottom, it goes to 4 minus 0. Okay, and that's equal to 2 over 4, which is equal to 1/2, which is definitely less than 1. Okay? So even though I don't know what this series here converges to, I haven't figured that out, I know it converges because the ratio test says it's less than 1. So the ratio test implies convergence. Okay, the ratio test implies convergence here. And that is really not that difficult to do a lot of the time. The only thing that can be really a pain is when it turns out to be 1, okay, which will sometimes happen. Okay, so let's have a look here. There's an example here in the notes which is a little bit unsuitable because it's a geometric series and we already know how to do that. So I think I will stop this video here, and I will give a video doing an exam question in the next section, and that should give you everything you need to be able to answer a question on this for assessment. Okay, take care everyone. I hope this finds you well, and I would remind you that any questions you have, you can ask me. I will do my best to help. Okay, thank you everyone. Bye.